Ayan. So once again, good afternoon to everyone. So if you haven't yet, check the chat box. So there is the link ng ating attendance. Kindly fill that one up so that you know, so that I know that you are present for today. So while you're filling that one up, so let me go over our agenda for this particular synchronous session. So for today, we'll cover the following. So activity is gonna be the first thing that we'll do for today, followed by the lesson proper. So in the lesson proper, we'll expound on the questions posed in our activity earlier. And finally, all other announcements and questions that you have regarding our course. So by the end of this learning guide module, we should be able to achieve the following target outcomes, namely, define the second law of thermodynamics, describe the degree of disorder of a system, and compute for the entropy change of a reaction. So those are the things that we aim to achieve by the end of this particular session. So at this point, I think naman that we've already filled up the attendance. You can just fill up the attendance later na siguro if you haven't yet done so. In the meantime, so I'd like to request everyone to please go to menti.com and use the code shown on the screen to participate in our activity for today. So that's menti.com using the code 81877845. Again, that's menti.com and use the code 81877845. So to warm up our idea for this activity, so let's start off with just soliciting your ideas for this one. So on the screen, you should be able to see the menti.com and the code as well. So to warm up, so I'd like to solicit your ideas first. So what is your idea of entropy? So kindly fill in your answers for this one. For the others, please now join the menti.com and use the code that you see on the screen. So just a very brief idea, menti.com only accepts a limited number of characters. So just your very brief idea as to what entropy is all about. So 7 people pa lang, 8. So can we have the rest of the class participating for this one? So just what your idea of what entropy is all about. So far we have half of the class. So perhaps the rest can participate. Let's just give them 1 minute more to enter their idea of what entropy is all about. Okay, so I think that covers the class na. So from the answers that I see in here, so what stands out to me are the following. So I have here the energy that can't do work, okay, unavailable energy, heat loss to the universe. So those particular na ideas, they kind of touch into the ideas that were introduced in the video that we have. So as for the others, thank you so much for your ideas. So I think we're now ready to move on. At this point in time, you might want to have your calculators ready to be able to answer the problem solving questions down the line. So moving on to question number 2, we have a multiple choice question. So we only have 17 players. Can we have more people? So please do participate in this one. So start pa lang naman ng year. So I can't yet spoil this one, but so spoiler alert at the end of the year. So I'll be tallying the points that you get in the activity, and whoever gets the highest points will get a small prize from me. Ayan. So at least naman engganyo naman tayo mag-participate, ano? So the others, kindly please catch up with us. So go to menti.com and use the code 81877845. Okay, my laptop is feedbacking a lot. Sige, so there's already 22 participants. So I think we're now ready to start. Maybe the others have difficulty with their connections. So that's okay. Maybe next time they can participate. So we have question number one. So which of the following phrases best describes a spontaneous process? The first choice, it is fast. Second choice, it is slow. Third choice, it proceeds without assistance. And fourth choice, it requires energy input to drive it. You would still have about 10 seconds to answer. 3, 2, 1. Time's up. Let's see what our answers are. So the majority of the class answered the third choice. So that is correct. So when you're talking about spontaneous processes class, so it talks about processes that proceed without us having to do anything. So it just proceeds on its own without us having to do any intervention. So no energy needed to be added to drive that particular na process to happen. However, just because we have a spontaneous process does not mean that is going to be a fast process or a slow process. So how fast or how slow it is has nothing to do with its spontaneity. So congrats on the 9 people who got that one correct. So moving on to another multiple choice question. Which of the following best describes an irreversible process? You have a couple of choices on the screen. So first choice, non-spontaneous, reverse spontaneous, and reversible. Second choice, spontaneous, reverse is spontaneous and reversible. Non-spontaneous reverse is neither spontaneous nor reversible. Spontaneous reverse is neither spontaneous nor reversible. Spontaneous has no reverse process, or non-spontaneous has no reverse process. So we're quite evenly distributed in this one. So the correct answer is when you have an irreversible process class, that is a spontaneous process whose reverse is neither spontaneous nor reversible. So it only goes in one direction. So the other direction is gonna be something that you actually need to do an intervention for that one to happen. So that is an irreversible process. So we have 3 people who got the correct answer. So congrats on that. You three. So here we have the following na question. So please complete the following sentence. When delta S of the universe is greater than 0, meaning positive ang value, an irreversible process is blank. So kindly complete the following sentence by putting in a word for the blank. So while we wait for the others to answer, please get your calculators ready for the next na questions. So we have 22 participants. We're still waiting on 5 more people to enter their answer. So let's just give them 30 more seconds to enter their answer. When delta S universe is greater than zero, meaning it's positive in value, an irreversible process is blank. Okay, so looking at the answers in here, so most of the answers say na to complete the sentence, the irreversible process is spontaneous. So that one is correct. When you have a delta S for the universe greater than zero, that will tell you na that the irreversible process is a spontaneous one. So note lang on the spelling, there's one person na na wrong spelling lang ng spontaneous. Ang continuous din also, spelling as well. So pakibantayan that one. But in any case, so congrats on getting the correct answer for this one. So delta S universe gives us a spontaneous, irreversible process. So at this point, I hope you have your calculators ready. So let's now go to our question number 3. So a process occurring at 25.9 degrees Celsius absorbs 5.61 kilojoules of heat. The question now is, what is delta S of the system? So you still have about 45 seconds to answer. So only a handful of people have answered. You still have 10 seconds to answer. And time's up. So let's check our answers. So the correct answer here is 0.0188 kilojoule per Kelvin, or an alternative answer would be 18.8 joule per Kelvin. So I think we just have some rounding off error in here. So this one, dapat gi-round off lang siya and wala siyang unit as well. So di siya considered. This one, again, rounding off error ata ito. Kaya siya hindi na ano. So that should be 18.8 joule per Kelvin. So sige na lang, better luck next time for this one. So hopefully we can do a little bit better with this one. So please take note of the answer earlier. The correct answer was 18.8 joule per Kelvin. Now for a process in here, delta S of the system is negative 8.9 joule per Kelvin, and delta S of the surrounding is negative 10.4 joule per Kelvin. The question now is, what is delta S of the universe? You still have 15 seconds to answer. Okay, one person lang ang nag-answer. Okay, this is a bit concerning. Sige lang. So let's see what the correct answer here is. Okay. So the correct answer is negative 19.3 joule per Kelvin. Again, please be mindful of your unit always. Pag walang unit, hindi siya counted as a correct answer. So we have one person who got the correct answer for this one. And we have question number 5. So based on your answer in the previous question, is the process spontaneous or non-spontaneous? So hint, the answer earlier was negative in value. So that should tell us na it is a non-spontaneous na process. So we have 5 people who got the correct answer for this one. So medyo marami-rami ang nagkamali na ang answer dito. So since negative ang answer earlier, so that should have told us na that was a non-spontaneous process. So looking at the scoreboard, so we have the following. So leading the pack with 2,886 points is May. Congrats, May, for getting the top score. And following her are Adriel and Vince as well, rounding up the top 3. So congrats, guys, on getting a high score for this one. Again, these scores here will be noted and tallied at the end of the school year. So the one with the highest score in the class will get a little prize from me. So stay tuned na lang as to what that one is. So thank you for participating in the activity. So looking at our performance, so I think there's a little bit of difficulty with the topic at hand since there were a lot of people who didn't get the correct answers. So let's try to go into the topic for today. So basically, we've already introduced at this point our internal energy, which is a way for us to relate the amount of heat that we put into the system and the work being done by the system to the change in its energy. So we already knew that the internal energy is actually actually more useful for constant volume process, but what we commonly encounter are constant pressure process in our day-to-day lives. So this is where our enthalpy comes in. So the enthalpy introduces our PV work in the equation. So our enthalpy is related to internal energy by the equation delta H is equal to delta E plus P delta V. So the delta H is very useful for constant pressure processes. And it is by simply measuring the heat in a constant pressure process that we're now able to determine ano bang delta H natin. that allows us a way to be able to measure the change in energy of the system. So that's what our alternative activity was supposed to do. So it was supposed to help us be able to measure the delta H in a laboratory setting using the coffee cup calorimetry. So all that is well and good. However, our delta our internal energy and the enthalpy does not allow us to be able to tell whether a process is gonna be a spontaneous process or not. So when you're talking about spontaneous processes, class, so these are processes that occur without any outside assistance. So no outside assistance, it occurs in a finite amount of time. So meaning it doesn't take forever to happen. And it is happening under the existing conditions. So it's possible naman na a particular process right now is not spontaneous, but changing the conditions, it can then be made spontaneous. An example of that would be the freezing of water to make our ice. So at existing room conditions, so in the heat of our room, we don't expect our ice to just form by itself without any intervention. But if you lower the temperature of the room, so we might possibly be able to form the ice just by changing the existing conditions. Now, the idea of the second law of thermodynamics, so it actually supplements the first law. The second law states that for all real processes that occur spontaneously in the direction, they always tend to increase the entropy of the universe. That is to say, the entropy of the system plus the entropy of the surroundings. So this is highlighted for you in equation 12. So why is there a need to be able to actually have our entropy and the second law of thermodynamics to be talked about? So let's delve a little bit deeper into the first law. So our first law is well and good in being able to tell us ano ba ang change in internal energy of the system. All you need to do is know the value of Q. Like in this scenario, you can just measure the amount of heat leaving the coffee cup, and you can now be able to measure ano ba ang change in internal energy of the system. However, our first law fails to be able to explain to us why it's scenario 1 that is happening. Namely, the scenario 1 wherein ang coffee natin, as you just leave it on the countertop, so it cools down as time goes by. It does not explain to us really why our coffee does not just heat up on its own without us having to do anything. So it doesn't give us an explanation why scenario 1 is a spontaneous process, while scenario 2 is a non-spontaneous process. So that is the importance of our second law. It now enables us to determine out of the many possible processes in the universe, ano ba ang spontaneous in a given condition and what processes are not spontaneous. So the criterion for a spontaneous process would be that the delta S of the universe is going to increase. That is to say, delta S universe is greater than or equal to 0, as said in equation 12. So we have a couple of people who have given us formulations of the second law. So from the studies of Carnot, we were able to come up with the following conclusions. namely that heat is spontaneously transferred only from regions of high temperature to regions of low temperature. This experiment has been done over and over again, and never have we seen na the heat spontaneously transfers from the cold region to the hotter na region. That simply does not happen. So this is basically the root of Carnot's experiments. Building on the ideas of Carnot from his Carnot heat engine, so Clausius also came in with the following statement as well, which tells us na you cannot have a refrigerator. A refrigerator here, by the way, is just the opposite of a heat engine. So kung heat engine kanina is this one, heat is being transferred from the hot reservoir to the cold reservoir. So when you're talking about the refrigerator, it's the opposite. In a refrigerator, it's the heat that flows out of the cold reservoir into the hot reservoir. So baliktad ang pag-operate niya. Now Clausius tells us na this cannot happen. The heat cannot transfer from the cold to the hot region without the input of an external energy in the form of work. So that is basically the Clausius statement of the second law of thermodynamics. From here, we're also able to define the reversible and irreversible processes. So when you're talking about a reversible process, it's any spontaneous process whose direction can be reversed to return the system to its original state by some immeasurably small change to the property of the system. In this case, itong property that we're talking about is the temperature lamang. So just by varying the temperature a little bit lamang, just having a very small increase in temperature or a very, very small decrease in the temperature, we can return the system to its original state. That's the idea of a reversible process. Reversible processes are represented as follows. So when you see this double hook arrow in here, so that is an indicator to you na we're dealing with a reversible process. This hook sa taas, pointing from left to right, this is the forward process. And the one at the bottom, the one that points from B to A, is now our reverse process. Now, an irreversible process, as what we have seen earlier sa activity, is any spontaneous process whose reverse is actually neither spontaneous in the given condition nor reversible for that particular na condition as well. So that's what we mean by an irreversible process. And finally, we have yet another statement of the second law. So we already have galing kay Carnot. We also have from Clausius. And we now have this statement from Kelvin. So it is in his honor that we name the Kelvin scale ng ating temperature. So according to the Kelvin statement, we have the following. So according to Kelvin, it is impossible to convert the heat completely into work without any other effect. So this has major implications, class. So later on, if you're going to be scientists in the future, what the Kelvin statement tells us is that you cannot design an engine that is actually capable of transforming the heat input 100% into useful work. Some of that work is always gonna be lost into the universe, and that lost heat is what we call as our entropy. So entropy is the measure of how much heat per unit temperature is unavailable to us for doing useful work. So the change in entropy for a reversible process is defined by the following equation. So it has major implications on how effective our machines can be. So we cannot have a machine that's gonna be 100% because if 100% efficient siya in converting the heat to work, so it already violates the second law of thermodynamics. And based on numerous experiments since the time ni Kelvin, we haven't yet seen one thing in the entire universe that violates the second law. So we're never gonna be able to make a perfect machine ever with 100% efficiency. So the earlier equation talks about the reversible process, but for an irreversible process, the equation is varied as follows. So the delta S for an irreversible process is equal to the Q reversible over the T. Take note of the units here. Ang Q natin has the unit of joule. Ang temperature always has the unit of Kelvin. So joule divided by Kelvin, that's the unit of the entropy. Or pwede rin naman, you can just have the Q having the unit of joule per mole. So joule per mole divided by Kelvin, you have joule per mole Kelvin. So either way, you have a joule on the numerator and a Kelvin on the denominator for the unit ng delta S. So generalizing this one, so for any spontaneous process, mapa-reversible man iyan or mapa-irreversible, we now have equation 13 to use. So delta S is always gonna be equal to or greater than the Q rev over the temperature. The temperature na sinasabi dito is the temperature in Kelvin. So we can summarize equation 13 to tell us the following. So if you have any spontaneous process that is reversible, delta S of the universe is always equal to 0. Meanwhile, if our spontaneous process is irreversible, we expect that delta S universe is greater than 0. Pag less than 0 na yan, then we're already having a non-spontaneous process. So now let's try this example. So this one was asked in our activity. So example 1. A process occurring at 25.9 degrees Celsius absorbs 5.61 kilojoules of heat. The question now is, what is the value of delta S of the system? So as always, with our problem solving, we start off by summarizing all the given information. So we're given the following data to use. So una-una ang temperature. So can you remind me again, how do we convert ba the temperature from Celsius to Kelvin? Can anybody tell the class how to do that one? How do we go about converting degrees Celsius to Kelvin.
Mag-add lang, sir.
Okay, so Yisha says na mag-add tayo. So Vince also raised his hand. Vince, would you also like to chime in?
Yes po sir, mag-add po ng 273.15 po sa Celsius po.
Okay, so both are correct. So get the temperature in Celsius and add 273.15. So this one, so typing this in, so can you please compute for me how much ang ating temperature in Kelvin for this one? Okay, so Phil has his answer, 229.05 or point 0.5 rather.
0.05 po, sir. 299.05.
Okay, please don't forget to put in your unit always. Hindi pa naman final answer, so no need to round off for this one. So pwedeng iwan lang natin siya as is. Aside from the T,
Ay,
Kaori
sir.
also got that one correct. Yes, please, go ahead.
Dili siya 229.
299
Okay,
po,
how much
sir.
did this was?
299.05.
Okay, so thank you for the correction. So that's the temperature of our process. Also given here is the heat. So Q is equal to 5.61 kilojoules. So ang sabi dito, class, is that it absorbs that heat. So from absorb, do we mean to say na ang Q is positive or Q is negative? Can anybody recall? Is Q positive
Positive
or
po.
negative? Okay, thank you so much. Pag absorb, that tells us that Q is positive in sign. Or we can also express this one as positive 5,610 joules. So through all this, what we're supposed to find is the following. So we're now supposed to find the value of the delta S for the system. So to do that, it's a very simple thing lamang. All we need to do is just substitute our values. So we have positive 5,610 joules divided by our temperature of 299.05 Kelvin. So can you please compute for me, how much will this one be equal to? Okay, so we have Bea, we have Kent with their answers. So trivia lang, by the way, I forgot to emphasize it earlier. So dito, let me go back muna, let me backtrack. So if we consider the Kelvin statement pala, I forgot to mention it earlier, our common engines, the ones that power our cars and other vehicles, ang kanilang efficiency is around 25 to 30%. You might imagine that's not much. But actually, using our available technologies, that's really the highest that we got. So when you're talking about car efficiencies, so kakaunting percentage lang ang kaya nila na iangat. From 25, maybe mga 1% lamang at most, if we're optimistic. Again, the reason why we cannot have 100% efficiency with our cars is due to the Kelvin statement. So that gives us a limit as to how efficient our engines in real life is gonna be. So let's check the answers. So we have a couple of answers on the chat box. So in here, the final answer for this is equal now to 18.8 joule per Kelvin. So again, please always encircle or box your final answer so that your teacher will find it easy to find your answers always. And also, don't forget to write your unit. That's very important. And always express your final answer to the correct number of significant figures. 5.61, that is 3 significant figures, excuse me. 299.05, that's 5 significant figures. So in our final answer, we should only have 3 significant figures lang dapat. So always observe the correct number of significant figures. So that is example number 1. So far, any questions on how we answered example number 1?
None po, sir.
Okay, thank you. So John also, so let me point out lang, capital letters always ang ating joule and ang ating Kelvin. Small letter J and small letter K mean a different thing, particularly in our physics and chem. Yes, please, may nag-raise ang hand.
Sir, ganiha god. Kuan na gito. KJ tong unit. Tapos, wala na niya gi-convert to joules tong KJ. KJ per K.
Okay.
Ay, itong
Sige.
sa mente, sir.
Either answer is actually acceptable. So you can always have, if you haven't yet converted the value ng Q, you can have instead the value of this one, which is 0.0188. So either answer is actually acceptable. Okay, so does that answer your question? Oops.
Opo, sir. Thank you, thank you.
Okay. So next time also, let's try to really, when we're participating, let's try to be able to speak in English. Doesn't have to be perfect. Kailangan lang talaga natin i-practice so that we're able to communicate to the widest possible audience our ideas. So in any case, thank you to that one. Thank you for that good question. We also have example number 2. So this was again taken from our activity earlier. So from this one, so given the following data, do we have a process that is spontaneous or non-spontaneous? So to answer that question, once again, we have to summarize all of the given information. So copy ko na lang. And from this, we're supposed to determine whether it is spontaneous or not. So as what we have seen in our equation number 12, way earlier, so the delta S of the universe is simply the sum of the delta S for the system and the delta S for our surroundings. So let's compute for this one. So copy natin iyon. So let's copy that equation now. We have the following. So typing in our values now, we have the following values. For the delta S system, that's negative 8.9 joule per Kelvin. And for our delta S surroundings, we have also fine. Negative 10.4 joule per Kelvin. So can you please add this one for me? So how much bang value for this one? Okay, so Chelsea and Max have their answers. So this is negative 19.3. Sandra also with her answer of negative 19.19 lang rather. So the value that we report should be having the least number of decimal place since addition naman ang pinag-uusapan. Negative 8.9 we see has 1 decimal place. Negative 10.4, mayroon siyang 1 decimal place. So it follows na our final answer should have 1 decimal place as well. So since negative ang value ng delta S universe, we therefore say the process is... Yes, Chelsea, question?
Sir, hindi na po siya mag-follow sa amount of significant figures, sir.
Okay, good question. Adding and subtraction, decimal place ang basihan. Multiplication, division, ang significant figures.
Okay po, sir. Thank you po.
Okay, thank you for that question, Chelsea. Sige raw, can you please tell me, so based on this value, what do you think? Is the process spontaneous or non-spontaneous? So we have Kent and Vince with their answers. Can we have other people with their answers as well? Kurt as well says non-spontaneous. Same with Chelsea. So all of those answers are correct. When we have a negative value ng delta S universe, so as Sandra also mentions, we have a non-spontaneous process. So para maging spontaneous siya class, what we need is the delta S universe should be at least equal to 0 or greater than 0 for it to be considered as spontaneous. Now, being able to measure our entropy, like our internal energy and enthalpy, so entropy is not a quantity na we can measure directly. We can only measure the delta S for any given na chemical reaction or physical process. And luckily for us, to save us the effort of having to do the experiment ourselves, we can always look at our textbooks or other sources of data for the values ng delta S. The delta S is already tabulated, and we can now use a computation similar to Hess's law to be able to determine ano bang change in entropy for any given na process. So let me share our textbook for the meantime muna. So our entropy, you can find questions to this one in chapter 20 of our textbook. So entropy questions can be found in chapter 20, internal energy, enthalpy, calorimetry, and stoichiometry, and Hess's law as well. All of them are in chapter 6. So those are the two chapters that we're interested in at the moment. Now scrolling down further, away from chapter 6, for the enthalpy, internal energy, and Hess's law, and also away from chapter 20, which talks about our entropy and other things, we can now go to Appendix B. So Appendix B is a compendium of values. So we can see here that for every substance that we have listed, we now have the values ng delta HF. So it's useful for our Hess's law. And we also have the value for the entropy. Now the entropy here is listed with the value of joule per mole Kelvin. So looking at something like, let's say, C, barium solid. So barium solid, it has the following value. For delta HF, it's equal to 0 since it is in its elemental form. And for its entropy, ang value niya is listed here as well. So that's 62.5. So we can then use Appendix B to be able to find ano bang entropy value for any chemical species that are involved in our process. So we're gonna be using this one to answer our problem number 3. So example number 3, so we now have the following. So we're now asked to calculate the delta S at standard state. Again, the degree symbol here stands for the standard state. So, quick review. So, can anybody recall for me, ano nga bang meaning ng standard state again from last meeting? So, can anybody recall what we mean by standard state?
Yung sa 25 degrees Celsius po something, sir.
Okay, so that's correct. So one of the conditions ng standard state is 25 degrees Celsius siya. So there's another condition. Can anybody recall the other condition sa standard state?
Yung 180 amps, sir.
Okay, thank you so much. So that's correct. So when you're talking about standard state, that is at 25 degrees Celsius and at 180 M. So tama-tama, since we already have the values listed in our Appendix B for this one, so we're now able to use an equation very similar to our Hess's law to be able to compute the change in entropy. So its equation is something like this one. So we first sum up the entropy of all the products times their stoichiometric coefficient minus the summation of the entropies of all the reactants times their stoichiometric coefficient. So what we need in here, aside from the values in Appendix B, is we need the equation for the combustion of ethane. So sabi dito, ethane combusts to form carbon dioxide and gaseous water. So again, when we say combustion, we always refer to a reaction with oxygen. So type ko na lang for this one. So I have in here my C2H6, the ethane, reacting with my oxygen. Both of them are in the gas phase. To be able to form the CO2 gas and the gaseous water. So the products here are CO2 and also gaseous water. So please always remember that one ha. When we're talking about combustion, we mean to say na it's a reaction with oxygen. So that should give you a clue as to what reaction we are talking about. Now looking at this one carefully, parang hindi pa siya balanced. So let's try to balance this one out. Sa carbon dioxide, so we need to multiply a constant in here. Can anybody tell me, ano ba dapat ang coefficient ni CO2 for this one? Okay, so Vea is correct. Since meron tayong 2 na carbon sa reactant side, the product side should also have 2 of the carbon. Kaya tayo may coefficient na 2. How about for the hydrogen? What do we need to put in here para lang same siya as the number of hydrogens in the reactant side?
3 po, sir.
Okay, thank you, Chelsea and Vea and Kat as well. So this is supposed to be equal to 3. Balancing off, finally, the oxygen. Oxygen always ang pinakalas na i-balance. So meron tayong 2 times dalawang oxygen here. So that's 2 times 2 giving us 4 plus 3, that gives us 7. Para magkaroon tayo ng 7 din on the reactant side, we have to multiply here 7 halves. Since we can verify this one, 7 halves times 2 gives us 7 na lamang. So pareho ng 7 ngayon ang ating oxygen sa reactant and sa ating product side as well. So that is our balanced na equation. So with our balanced equation already put here, so we can now use our Hess law type na equation to be able to compute the delta S. So for this one, what we can do is copy muna natin ang coefficients ng lahat ng products. So we have 2 moles for the carbon dioxide. Times ang entropy niya, which we'll look into in a little while. Plus, for the gaseous water, we have 3 moles times the entropy in Appendix B. From this, we subtract our reactants. So reactant natin, meron tayong C2H6. Coefficient niya is 1. So we have 1 mole of the C2H6. Times its entropy listed in Appendix B. Plus, for the oxygen, we have 7 halves. Moles. Now with our oxygen, so we're already certain anong value niya. Since oxygen in the standard state that we find in our day-to-day life is in the gaseous state, ang ating oxygen we expect has an entropy, or rather entropy pala ang pinag-uusapan. So we just have to look at it as well. So never mind that one. So let's try to look at these one by one. Starting with carbon dioxide, then water, then we have C2H6 and O2. So transfer tayo kay Appendix B. We have CO2 gas. CO2 gas, it's over here. So the entropy is here under the third column. CO2 gas, if we look at it carefully, fine. Its entropy here is equal to 213.7. So let's copy that one. To 13.7. So the unit here is joule per mole Kelvin. So let's copy that one as well. Plus, for our water, so again, hanapin na natin siya. Again, remember that the entropy, nasa third column siya dapat. So gaseous water, so where is it now? Water. Ayun. So gaseous water, we find it over here. And looking at the table, its entropy is equal to 188.72. So by the way, please always be mindful of the state of your water. Ang water, dalawang listing niya dito. You have water gas over here. And meron ka ring water na liquid. So it's always important na we know what state of water we are talking about. Because if you mix these two up, so masyadong magkaiba ang values ng kanilang entropy. Water gas is 188 and the water liquid is 69.9. So always be mindful of the state for that one. Oxygen, tamang-tama, may value na rin siya dito. So let's copy that. We have 205. 205.0 joule per mole K. And C2H6, that's our remaining na reactant. So looking it up in our table, C2H6. Nasa carbon siya dapat nakalista. Ayan. So C2H6, that is 229.5. So with these values in here, so can you please compute for me how much bang value ng ating delta S for this reaction? So kindly compute for me, please, how much is the delta S at standard state for this reaction? Okay, so Chelsea with her answer. Capital J for Jules, John. So please don't forget the proper capitalization. Okay. Can we have one other person to verify the correct answer? So Jameer also with his answer, which is 46.56. So for this one, our answer is equal to 46.56. Notice here that the unit ng mole for each term cancels out the mole in the denominator for the entropy. So, ang matitira na lamang is joule per Kelvin. And finally, to be able to express this one to the correct number of significant figures. So since we're talking about addition here mainly, so this one has 1 decimal place. This one right here that I'm highlighting has 2 decimal place. This has 1 decimal place. And this also has 1 decimal place. So in our final answer, dapat we drop the 6. And since 6 is greater than 5, we're going to round up the last remaining digit. So our final answer is 46.6 joule per Kelvin. So that is how we find the entropy for any given reaction. So to do this, we just have to use an equation similar to Hess's law that we've talked about last meeting. So these values, they would be given to you. And if they're not given, we can always consult our Appendix B ng ating textbook. In Appendix B, under sa third column, here is where you'll find the values ng entropy in units of joule per mole Kelvin. So these are the values that we'll use to be able to compute the delta S at standard state. So for this one, in example 3, so nagets lang ba how we answered this one? Okay, so Chelsea says yes. How about the others? Na-follow lang what we've done for example 3. Okay, thank you, Sandra, Sophia, Vince, Ivan as well. So notice in here, if we're only interested to find whether spontaneous siya or not, we can just simply look at how many gas molecules are involved in here. So without having to compute the actual value, we can actually be able to predict whether spontaneous ang reaction or not. So how do we do this without having to compute the delta S value using the value in our Appendix B? Bibilangin lang natin how many gas molecules are in the product side. So meron tayo ditong 2 gas molecules in the product side for carbon dioxide plus 3 water molecules na gaseous state as well. So 2 plus 3 gives me now 5 gas molecules. And to that we subtract how many gaseous molecules did we start off with? C2H6, so gas pa rin siya. So that is 1. So that's 1 plus, for the oxygen, this is 7 halves. Let me just copy this one properly. So simplifying this one, we now get, for the products, meron tayong 5 gas molecules, minus, for the reactants, meron tayong 1 plus 7 halves. So that's 9 halves. So this difference, we'll call it as delta N. Delta N symbolizes the change in the number of gas molecules. So very quickly, can you compute for me how much is this one? 5 minus 9 halves. Okay, so we have the answers from Max, from Bea, and Chelsea. Delta N is equal to 1/2. So from the value ng delta N, if ang delta N natin is greater than 0 or equal to 0, we now have a spontaneous process. Otherwise, if the delta N has a negative value, that is to say it's less than 0, this is non-spontaneous. So since greater than 0 ito, we now say that, therefore, the combustion is spontaneous. So just by looking at the balanced chemical equation, we already have the conclusion without having to compute ano bang value mismo ng delta S. And since spontaneous ito, we also expect that ang delta S here is, greater than 0. Okay? So we're already very short on time. I didn't realize how fast that time flew. So, what we're gonna do na lang, so to those people who had questions earlier, so please message me na lang, either sa ating GC or you can just message me privately na lang. So please always check K-Hub for the announcement. And in any case, thank you for your participation today. So I hope you've learned something from this session. I hope we were able to appreciate the importance of our entropy and the second law, and also how to compute that one. So again, time really flew, but in any case, so please enjoy the rest of your week. Stay safe always, and see you next time.
Thank you po, sir. Bye po, sir.
Thank you po,
Thank you,
sir. Bye po.
sir.